Good day. Today we start our lecture number 7, and this deals with the compound stresses in machine parts. If we see our earlier lecture, then we have learned that the elements of a force system acting at a section of a member are normally axial force that we are given by sigma equals to P by A, bending moment sigma equals to My by I, shear force Vq by It. Please note that we can have this T is the thickness, what we consider there as B also the width of the section. Same thing here, it has been written as T. Although this particular beam acted upon by loads P1, P2, P3 etc. And do not have any torsion acting onto it, but still we have written down the equation for the torque, that means which gives the shear stress is Tr by Ip. In short, what we mean to say is that this is as a recapitulation of all the forces that we normally come across when the machine member is subjected to varieties of loads. Now, today we will be considering, the name suggests as the combined stresses, means if all this type of various type of stresses arise at a point in the machine member, then how we combine them together to get some ideas that what is the effect of all the stresses that is coming onto the machine member. Now, apart from the stresses what we have discussed in the last class, or rather last two classes, there are also other two categories of stresses. One is called bearing stress. Now, this stress, as you can see, is defined as the compressive stress developed when a body is pressed against another. Now, here we have seen three examples. That first of all, you can see a simple circular member which you have defined as a pillar having an area of cross section A is getting pressed over another, say, floor or something like that under an action of load P. Then what we call is that at this juncture or at this location the body is pressed, so thereby the bearing stress sigma, here we are calling as sigma, equals to P divided by A. Please note that if we had written an expression for compressive stress, that means if we have written an expression for compressive stress, then what we can see is that the same figure if we draw, and it is loaded by an force P, then at this we are getting what we called as the bearing stress at this location, and that has been given as P by A. Now, if we have a cut at any location here, and if we have taken a free body diagram, then what we would find out, that this particular body would have again come under a load P like that, and in that case the compressive stress is again defined as P by A. So, this compressive stress having the magnitude is P by A, and this bearing stress is also having a magnitude P by A. Then please note that when we call bearing stress, then it is only where the contact is taking place between two different machine elements, whereas compressive stress is nothing but an internal stress. So, here lies the somewhat a difference between an compressive stress and bearing stress, although in certain cases the expressions for the stresses might be looking the same. Now, In the same way, if we look into the second figure, then what you are getting? You are getting that this is a shaft going inside a hole having a length L, and this is pressing the shaft, this particular member is pressing the shaft with a load P. Therefore, what is this thing? In that case, the bearing stress sigma is written as P divided by length L into this particular diameter or diameter of this particular shaft. Okay. Now, that means what you mean to say is that if we are considering this, that means whenever there is a hole, if we exerted the shaft inside, that means if we are making a hole something like this and the shaft is going, then we assume the contact to be taking here, and it is only the projected force that we are interested. That means, although we can see that this particular one, if we look to the actually the situation once again, we can represent that somewhat perpendicularly the forces are acting like this. But what we are taking, all these force projections something like in the normal direction, means all the forces in the normal directions. So, thereby in that particular expression we found sigma B. I think it was written as sigma, it does not matter, it is the same thing we mean to say, equals to this load divided by this is the length L that is coming into picture, and this is L, and we always use this is the diameter. So, this is the projected diameter T. So, this becomes a bearing stress in case of the circular hole. So, you remember, whenever there is a circular hole and we are having a contact of the short just described, we always take the area as a length and the projection. So, if it had been a small plate of thickness T, suppose we are having a small plate of thickness T and we are having a shaft inside like that, then what is the projection? Here also we will be considering T into diameter of the shaft. This is the projected area. So, this is the area to be considered for the bearing stress. So, if we look at the third one, then we can see that our shaft is again going inside a bush and it is locked, what we call as with a key, and the short and the shaft is transmitting a torsion T or the torque T. So, in that case we can see the sigma, the bearing stress arising onto this key is given as 2T by ALR. What is this actually signifies? That once again we can see that if we are having this one, then if we look into this figure, the shaft is there, this is actually T and so it is acted upon by a torque T. So, what is happening? So, we are having the radius, this is R. So, what is the force applied? Suppose it is considering force, then force equals to T divided by R, and then in this particular case you can see if we are applying a load like this, then this particular shaft is having tendency to rotate. So, obviously the shaft will be pressed over here by the key and it will be pressed over here onto the bush. So, this is the area where you get bearing. So, entire dimension was given as A. So, this length is basically A by 2. So, what is the total area? The area is equals to A by 2 multiplied by what you are getting is a total length. I suppose it was given as L. So, we are getting bearing stress sigma equals to force again divided by area, that comes out to be T, 2 goes up A L R. So, this is the precisely how we get the bearing stresses in this manner. Now, we have shown you just 3 examples. So, there could be any more examples for this one where you can, where in the machine design whenever you see a contact between 2 machine elements are taking place, then what you do? You consider what is the force acting onto it, and correspondingly you divided it by the area of contact, and that will give you the bearing stress. So, this is one kind of stress what we have seen is called an bearing stress, and which is just purely coming due to the contact between 2 machine elements. Now, if we and this one, the forces what we have seen, that is already we have seen earlier, that these are the forces, or these are the forces acting onto the machine elements, creating all types of stresses. What has been given here are all the internal stresses basically. So, we go back to the digital class once again, just one second. So, another form of the stresses is called the buckling. Now, what is buckling? We won't be discussing much about the buckling. Only thing we would like to say at this moment, that it is some sort of a stability sort of thing where the stress and other things are not coming into picture. Basically, when you are having a very long slender column and acted upon by an vertical load as shown in the figure, just it is given an P, then you can see that this slender column can have a tendency of bending like this, and which we call as an buckling. Now, in this case there is a famous formula called Euler's formula is there to find out a critical load, which is given by this expression where C is a constant, depends on end conditions, means this is hinged and free end, both end could be hinged, both end could be fixed on. There are various types of end conditions. Depending upon that one, you can have a value of C. And other thing, this is known to you, this is E is the Young's modulus, I is the moment of inertia, L is the length as it is defined over here. Now, the basic idea of this P critical is that when the P is more than P critical, this P is more than P critical, then you just, if you give a slightest push from either this side or this side, then what will happen? The column will completely fail. But if the P is less than the P critical, then with giving a slight deformation, I mean slight push at this side, and again if you just withdraw the force, that sideward force, then what will happen? The column structure will again regain to its original position. So, this is some sort of stability which comes into picture whenever we design a machine element having a slender, whenever we are having a slender column like that. One of the example you will be learning later on could be, say, a screw for a screw jack requires to be designed for a buckling load. This is just one example I am trying to give you. Now, here we take up one example of how a combined stress can occur in a beam. You can see that this is a cantilever beam and it is acted upon by a load P over here at the end having a length L, it is acted upon by a tensile load for F and a torsion, which is, if I view from this side, it is in a clockwise direction. You are viewing from this side, then it is coming out to be in the clockwise direction. So, in this case, what is happening, that you are having the stresses which could be calculated as we have seen earlier. Now, in this example, you can see the axial stress is sigma is P by A. So, obviously, this has got the force by pi d square by 4. So, this gives you the idea. Now, bending stress we have learned was m y by I. Now, if you substitute the values of the m, so P multiplied by L, that is, we are trying to consider the section just at the end, because we know that maximum bending moment will be occurring when L is a maximum. Okay. So, that is the distance is a L maximum, and we will be getting the bending moment at the end as P into L. So, if you substitute all the values, then we get an expression for bending stress as given over here. Similarly, the shear stress we know VQ by I B. In this case, what is happening, that we will be having the maximum shear stress at the diametrical location over here, and that is coming out to be how much, that this is P, means this is the P load. So, the shear stress V will be coming as P. Q, we have defined that first moment of area about the neutral axis, and so that means this will be the area for which you get the moment about the neutral axis will be Q divided by moment of inertia about the neutral axis, and D is the diameter of the shaft. And torsional shear stress was how much, TR by IP, and again if you substitute all the values of respective R and IP etc., then what you get an expression of the shear stress as 16 T by pi t cube. Now, what we can see in this figure is that we have selected some 4 locations. This is A. So, this is an A location, this is B location, this is C location, and we can call this as the D location. So, what are the stresses that will be coming at all these points? Now, if we look to this thing, then let us have an idea that what is the concept. We had got a P over here, and then just at the end, if we take a section like this, then it is a circular member, we are getting just a cut section we have considered. If I to be more precise, then let me do one thing. Means this is the view what you are getting, alright. That means this point is A. Let us assume that this is almost at the edge. This is B location, this is C location, and D is onto the other side. So, if we just draw and expanded view of this one, then what we can see? We can see that this is the view, and we are considering an element A. This is an element A. So, if we consider the torsional stress, so we have seen the torsion was in which direction? Torsion was in clockwise direction. So, onto this face it is anti-clockwise. So, obviously onto this face clockwise, shows shear stresses due to torsion. If we write down this T, this is D, this is B, this is C, comes out to be in this manner. And if we look to the vertical shear stresses, then what is happening? We are having, this is the shear stress due to the vertical load, this is the shear stress due to the vertical load. Now, what will be the shear stress due to the vertical load at this point? It will be 0, because the Q is 0 over here. Similarly, this is the vertical load over here, will be also 0. This was tau t and this was also tau t. Now, if we look to the bending situation, then what is happening? That you are getting some sort of situation that this particular bending stress, if you are considering over here, then it is coming out to be in it is in the axial direction. Okay. So, if we are considering this one, this face, if we see, this is the face we are seeing. That is, this is the element. Is it okay? This is the total element. If we consider, if we are looking the same thing. So, onto this element, what we can see is that this is the shear stress going like this, and this is due to a sigma axial, this is going like this, sigma axial. And what about that bending? Now, if it is bending like this, in this manner, it is bending like this manner. So, what will be happening? That you will be, if you look for the shaft, it is acted upon by load P somewhere here. We have taken the section here. This is the section here. So, this will be a tensile and this will be a compressive. So, obviously, if we look to the element A, then what is happening? That in addition to that, we will be having an imposed as sigma bending on the both the sides. This is sigma bending. Similarly, onto this face, which as a matter of fact we cannot see like, because this is the cut section. So, we have to see the surface. That means, if we look at the surface, that means if it is C where here, rotate it. So, C comes over here. Okay. It was here, you just give a rotation, C comes over here. So, that means what you are getting? This is sigma axial, and you are having a sigma bending in a compressive manner. And shear stress, it goes as it is. Okay. This is a shear stress because V was not there. So, in this manner, if we consider the just one element A, then what we get? We get this particular element acted upon, this is the element A, acted upon by an shear stress tau. We know that these two stresses will be complementary in nature, and we will be getting, this one is sigma axial and this is sigma bending. Similarly, we will be getting here the sigma axial and sigma bending. So, this is the entire state of stress at this point A. Now, if we go back to this figure and we see the summation, what we have learned from that example, the axial and torsional shear stresses are constant throughout the length because it is irrespective of the section. Now, the most vulnerable section is the built up end, that already we have discussed, because of the fact we will be always having the most bending moment at the built up end. There is no bending stress on the element B. Why? Because the element B falls onto the neutral axis, therefore, the fibers neither have any tension nor any compression. There is no shear stress on the element A and C. The bending and axial stresses act in the opposite direction on the element C, that we have already observed. So, for the safe design of the beam, we therefore consider the stresses on the element A. So, what we have learned? That means, when there is a machine member acted upon by several loads, first of all we have to find out, looking at the free body diagram, which is the most critical section. Now, once you have found the critical section, as it has been mentioned in this point 2, that we are having the most vulnerable section is the built up end. So, in that way you can find out which is the most vulnerable section, and for that matter you can find out the stresses at that point, or to be more precise, stresses at that section. Now, once you find out that section, there are several points onto the section, and in that circumstances again you have to find out which point onto that particular section has got the most stresses, and that we have found out here, that element A is the most vulnerable stresses. So, now we would like to find out that what is the combined effect of all types of stresses. The method, what we know, is called the method of superposition, means you superpose one stress over another stress. Now, in the superposition, what you understand is that you can superposition like type of stresses, means all the normal stresses can be combined together. In the similar manner, all the shear stresses also can be combined together. Now, the genesis of this particular superposition lies in the fact that the strain superposition due to combined effect of axial force P and bending moment M. This is just an example, that if we are having an axial force P and a bending moment M. Why this example has been chosen? Because axial force creates a normal stress and bending stress also creates a normal stress. Now, as because in design, what we know, that mostly all our stresses will be very much within the yield stress limit, thereby the amount of strain will be very small. So, it is possible that this superposition theory holds good. That means, it is possible to superposition all these type of stresses. So, looking from that aspect, we find that, say, just by putting an axial load, we are having an axial strain epsilon A, and we know if it is having a bending, I suppose if you are having, you can see the bending here is compressive, here is tensile, that means you are applying a bending moment in such a way, that means looking from this side you are applying, here is a clockwise and here is an anti-clockwise manner. Now, what is an imposed effect? Sigma epsilon A minus epsilon 2, and you are having this strain epsilon 1 plus epsilon 2. So, you can see the distribution of this particular bending strain and axial strain combined together comes out to be small amount of magnitude of the total strain will be less here compared to the magnitude of the combined strain what we are getting over here. So, from this, once we know the strain pattern, obviously the stress pattern will be obtained as we have seen earlier. From the stress equations we can find out the stresses, and that also can be combined together. But the basic idea is that you are summing up the deformations. Now, here also an example, we are seeing that axial force and bending moment is acting onto a beam. How the bending moment? This load P is creating a bending moment, and this force is axial force. The similar one as we have seen for the strain, there will be an uniform stress of delta F by pi d squared, and what will be the bending moment? My by I. So, that is m d by 2 is the y, and I is the moment of inertia over the neutral axis. So, this is the bending moment distribution. You can see an uniform distribution, these two magnitudes are same, and what you can see that this magnitude is superimposed. So, we are getting an added, this together will be a compressive load. So, this is an total minus, and all the next one is the plus and minus. So, that means you are getting an effect of this manner. So, that the net stress will be what? Delta F pi by d d square, and I think this would be 4 actually, and this will be md by 2I. So, if you add up this together, then you get the total stresses. Add up means the algebraic summation. So, what we can see is that this actually should be 4 f by pi d square. So, just make a correction please. Okay. Now, we go back to the next slide. Here we taken another example, a shaft transmitting power, where we are having the shafts are placed onto the bearings. There could be axial loads, and this is a torsion, that is a power transmission is taking place, and the actual load of the machine member or something is there, and for which you are getting an equivalent is getting a load P. So, any element or any section, if you consider any section over here, then any section if you take, and similarly if you take an elements like this, then what you get? You get this particular type of stress elements what we have seen earlier, and that will consists of what? The stresses of normal stress kind and as well as the shear stress kind. Now, the question is that we have learned that if we are having axial stress, stress due to axial force and bending moment, both are normal stresses, we can add up. Similarly, we can add up the shear stresses arising due to torsion and shear stresses arising due to what? Due to the shear, direct shear, or direct shear means a shear stress due to bending. Then what about that this effect of both the stresses, means namely the normal stress and the shear stress acting at a point on the machine element, what will be the combined effect? To learn that this particular combined effect, what we understand is that we have to use an idea which is called transformation of plane stresses. Now, to give an idea of the transformation of the plane stresses, let us use an idea. What we can find out here is that we have let us take up a element. Let this element be acted upon by a stress sigma x, stress sigma y. Now, this is tau x y, this is tau y x, this is we are having sigma y. What should be the stress? This will be, to have the equilibrium, we know the stresses has to act in this manner. Now, this is an element, this we call just like an element A, or what we understand, this could be element B. What we have just taken up in this particular what you call examples, we have this could be any element. Now, one important situation comes into picture is that if you are having this type of combination of sigma y and tau x y, I mean the shear stresses and the normal stresses, then we have to find out the combined effect of sigma and tau. Not only that, we have to also find out that if at that particular point at any other orientations, what is the stress? That means what is meant what is meant that this element is being acted upon by these loads. We know these loads, but if I make a plane cut through on some angle, say here I have just given as phi, then what will be the stresses at these locations? So there could be a possibility that although here we can see sigma x of some magnitude, at some other plane obviously the sigma x will change its magnitude, and those magnitudes could be larger than this sigma x what we can see apparently for this plane. Now this will create what? This will create a situation that at any particular cross sections what we can have, that you can have a stresses of different kinds. And similarly it holds good for the shear stress, that if we can see a shear stress acting onto this plane in this manner for any other orientations of the for any other orientation or any other plane, the shear stress also can take up a value which could be much larger than this value or which could be also lower than this value. So let us examine and find out what physically it means. Now what physically it means is that if I take a cut, let us draw this particular cut portion free body diagram. Okay. This comes out to be something like this. This angle is phi. This angle comes out to be how much? Sigma normal, because it is a normal direction, means we are considering this plane and we considering something like onto this plane we are considering shear stress tau, and this direction we are calling as a tangential direction. So this is the sigma y direction. Now without drawing any other figure, let us do one thing. Let us put the values of the write down the force values onto the plane directly. What is the force acting onto this plane? This will be just sigma into dAn. What is this? Normal area. What is the force acting due to the shear stress? This is tau into d sorry just tau into dAn. The force here acting as what? Sigma y into what is the corresponding area? The corresponding area we consider as dAy. Shear stress here will be as tau yx into dy. Similarly, what we get, the force in this direction is tau xy into dAx. This one is coming out to be tau, not tau, this is coming out to be sigma x into dAx. Is it all right? I think we have covered all the forces. So if this is the angle phi, then obviously this angle is also coming out to be phi. So if we consider the force balance, that means sum of forces in the normal direction equals to 0, just doing little bit of algebra, what we can write down, the value of sigma comes out to be how much? This sigma comes out to be half sigma x plus sigma y plus half sigma x minus sigma y into cos 2 phi minus tau xy sin 2 phi. Similarly, summation of forces in tangential direction equals to 0 yields that shear stress tau equals to half sigma x minus sigma y into sine 2 phi plus tau x y cos 2 phi. Now, while writing these equations, please note that we have taken this shear stress in these directions to be positive, means onto this x, this is x plane, it is positive. If we choose any point within the body, this shear stress is creating a clockwise moment. So, that clockwise moment is a positive one. So, this is clockwise moment, this is positive, this is taking into a negative direction. So, we are having a negative stress, and this is also a negative stress because it is creating a counterclockwise moment. So, under this situation or under these notations, we give the force equilibrium equations like this. Now, as we have been talking about that where is maximum or minimum normal oblique shear stress. Where is maximum normal oblique shear stresses, means which is the location we would like to find out. Now, for that matter, what we can do, simple mathematics, we can just simply take the derivative of this normal stress and the shear stress with respect to the angle, and thereby we can get the required relationship. So, this relationship if we find out, then we get that d sigma n by d phi we know it equals to 0. If we equate it, then we get minus sigma x minus sigma y sine 2 phi plus we get then we are getting this is as sine 2 phi minus, just one second, and this will be minus 2 tau x y cos 2 phi. So, this gives you an idea that this is coming out to be the idea, that means tan so what we get, tan 2 phi equals to minus of this tan 2 phi comes out to be minus of 2 tau x y sigma x minus sigma y. So, this relationship what you are getting is that tan 2 minus tan 2 phi tau x y sigma x minus sigma y. Now, of course, we are having two values of phi. We can see that we are having this phi, we are having two values at 90 degree apart. So, these are the two values we will be getting at 90 degree apart. And in the similar manner, we can find out also these values for the delta sigma n by delta phi. Now, one thing we can see that if we have just gone through that expressions what we have seen earlier, that under these conditions if you have just see that it is equivalent to the expressions what we have written for what? The expressions what we have written for the tau, shear stress tau. So, that means what we can say that whenever the values of the normal, that means as normal stress are maxima or minima, in that particular conditions we will be getting that shear stress values are coming out to be 0, because this expression is exactly the same as a shear stress expression what we derived just early. Now, we can see that delta tau by delta phi, once again if we equate to 0 and write down the similar expressions, then what we get? We get sigma x minus sigma y cos 2 phi, sigma y minus sigma y cos 2 phi minus 2 tau x y sin 2 phi. So, what we get? We get that tan 2 phi equals to simply coming out to be sigma x minus sigma y divided by 2 tau x y. So, this is the condition for which we get the maximum shear stress. Again also these two values will be, these two values will be 90 degree apart. That means, if you have noted down this one, I am just erasing the screen. That means, suppose we are having the ideas something like this, that we are having two values of angle, any angle which gives you, say this is sigma max, then obviously 90 degree apart will be having the sigma mean, and if you are considering the shear stress values, then this could be your tau max, again it is 90 degree, you are having the tau mean. So, this angle will be 45 degree. Okay. So, this is the idea, that means whenever you have sigma max, the 45 degree apart tau max, and the similar way you get for the other results. Now, if we go to this transformation of stresses, then what we have seen that condition for maximum normal stress what we have just derived, tan 2 phi is this one. Principal planes, the planes of maximum and minimum stresses, and no shearing stresses occur. That you have just remember that the planes of maximum and minimum stresses, no shearing stress occur, and principal stresses, maximum and minimum normal stresses are given by the relationship 1 and 2. 1 means the maxima and minima by this expression, means that if we put this condition into the main expression, then we will be getting and the relationship for the principal stresses in this manner. So, these are called the principal planes and these are called the principal stresses. What is the principal planes? Where you are having the maximum and minimum stresses and no shearing stress, and the corresponding values of the principal stresses are given by this expression. In the similar manner, what you are having, the condition for maximum shear stress is as tan 2 phi equals to this one, and the corresponding value of maximum shear stress is coming out to be this particular tau max. Now, if we go, then we can see the planes of maxima or minimum principal stresses are 45 degree apart from the planes of maximum shear stresses. Unlike the planes of principal stresses, at the planes of maximum shear stresses, normal stresses may act. Now, in this respect, one of the important situation comes out to be that a graphical solution. Now, in this graphical solution, if we look this as an element, as we have seen earlier, without going for this is a sigma x, this is sigma y, sigma x, then tau xy, tau yx, the same manner we get. Here you plot a sigma axis and tau axis. First you plot the values for this one. What is this one? Sigma x positive and tau x positive, because it is creating this clockwise. So, this is the positive. This value sigma y and this tau yx is negative, assuming sigma y to be less than sigma, that means this point is sigma x comma tau xy, and this particular one, if we consider this one, then we can find out this value as sigma y comma tau yx or minus tau xy. Anyway, you can write it down. You join these two lines, then draw a circle. These are the values sigma 1, sigma 2 principal stresses. You can see no shear stress, and these are the values tau max, tau mean. What is the angle? This always you call as control point. Now, from control point, how we are reaching this point? By say 2 alpha. So, we draw a line, come by here alpha, just make it half. Then this gives the value of sigma 1, I mean orientation of the sigma 1 as well as the value of the sigma 1, you can read it from here. So, obviously this comes out to the negative side. So, this comes out to be sigma 2. This is the orientation. What is the orientation of tau max? You can see, say this is 2 beta. So, from here you just go by a line beta. So, this gives you the sigma, this value sigma corresponding to this one is you are getting the sigma. So, you can complete that element, and onto this face tau max is positive. So, its direction is this way, this is tau max. So, tau mean will be just one second. So, tau mean will be this way. So, this gives you the values. So, this is sigma. Okay. So, this way of plotting a graphical solution, you can get it by plotting, this is called Mohr circle. So, this is a very useful way that if you wish to use a graphical solution, then also you can do it as I have described it here. So, we understand that to conclude today's lecture, what we can say, that we have already learned what? The compound stresses. Okay. Compound stresses we have learned, means sigma axial plus sigma bending, you can do it, correct. Then tau torsion plus tau direct or something like that, what you call, you can do it. Then you add up. How you do it? By transformation of stresses. This transformation of stress can be done how? That is, in addition to one is the graphical, just we did at the last, by graphical method, or by force equilibrium. equilibrium you can get this particular value. So, from force equilibrium and graphical solution you can get the values of the transformation of stresses. Once you get the values of transformation of stresses, then what you know, that you can find out stress at any point at any orientation for a machine element. This is a very useful information we will be carrying out for the design of the machine elements. Thank you. Good day. Today, as you have seen, that we are going to discuss about the design for strength. Now, we understand that when a machine part fails, when stresses induced by external forces exceed their strength. So, this is very quite understandable. Now, the only thing is that we have to look that what is the meaning by the word strength. The strength means, one we can notice is that the property of the machine element. Now, what do you understand by the property of the machine element? And suppose this is a machine element and which has been designed to take up some external loading onto it. So, once it has been designed, that whether it is put onto a machine member or it is simply lying onto the table or somewhere else, it is always going to have the strength for which it has been designed. See, I have chosen a material chalk, a simple chalk has been chosen, and we apply a pure torsion onto the chalk. Just you can see that if I apply a pure torsion, then it is little hard, so just see it has broken. Can you see the broken portion, how it has failed? So, it has just failed in the situation of this 45-degree line. I mean this both way, this is a 45-degree line. So, what is happening? If you consider this 45-degree line, can you not see it? It is resembling the same 45-degree line what we have drawn onto this particular plate over here. Okay. So, this is what is one small model I wanted to show you. Now, I will just have an explanation. Just see once again this particular plane. Okay, this is the plane you can see onto, this is the plane where you can see a failure, and correspondingly this is the plane where you can see the failure, and this is all at 45 degree as I have drawn onto this